at probability of some event. This is how probabilities are written. Capital P, parentheses of what you want to happen, stands for the probability of some event occurring. The probability of some event occurring would always be the number of ways of success over total possible ways. I'll use outcomes. Probabilities are always written as fractions, decimals. You don't have to write them as percents, even though that's still a legal, viable way of doing it. But remember, every time you go from a fraction or a percent, or a fraction or a decimal to a percent, there's an extra step, so there's really just no reason to worry about it. The probabilities are always going to be between 0 and 1. They have a range. They're never greater than 1. They're never less than 0. It's always less than 1, and it's always greater than 0. If a probability of something equals 1, if the probability of an event equals 1, what can you say about that event? It's gonna happen. Like, gonna happen. And that is the technical term, in case you were wondering. If it equals 1, it's a certainty. If you say off your phone and write this down, you would have heard me describe all this already. So put it in your pocket, because I have answered a lot of questions of you as of late that pertain to something I've already said. If the probability did equal 0, well, if it's not gonna happen. Ain't gonna happen. Not very many textbooks use this kind of lingo. I'm just, helping you out. So if you ever get a probability that winds up being like 6, you're wrong. You done goofed. We had this just recently in geometry, and there's some parts that people had a bit of an issue. Yes, sir?
So you said it has to equal 1, it's going to happen.
What happens is, if the probability equals 1, the event will occur. And I'll show you an
So if
example.
it's higher than 1, it's still going to happen.
No, it can't. You cannot have a probability greater than 1. All right, because the 100% means the event occurred. You can't make something occur more than it occurred. Okay. Let me show you. Remember yesterday when we did this, the probability of rolling, what did we say, a 3? If I take a 6-sided die, which is your standard number cube for you people that don't like to gamble, most books use number cube. Yeah, most books nowadays use number cube because dice in kind of leads you to the idea of gambling. Gambling's evil.
Wow, that's cool.
So the probability of rolling a 3 on a 6-sided die would be, well, how many successful ways can you roll a 3 on a die? 1. How many ways can you roll a die? 6. So the probability of rolling a 3 is 1 out of 6. Probability of rolling an even number. Right. The probability of rolling an even number, well, how many even numbers are on a 6-sided die? Well, 2, 4, 6. How many possible outcomes are there? And so on. Okay. What about the probability of rolling less than a 7? 100%. It would have to equal 6 out of 6 because I rolled the die. Unless the die miraculously explodes into nothing,
And the die dies.
Okay? And that's where this goes to. Now, we talk about it in terms of dice. We talk about it in terms of cards as well. And as we get into this more, that's why I wanted to just go right to probability. Remember how we did all those combinations and we did, certain hands that can be held? Not held, but you could get in terms for poker hands, those 5-card poker hands. Remember the one that we had where you had 4 aces and another card? We said that there were 48 possible ways of doing that. 4 choose 4 for the aces, 48 choose 1 for the other card. So in a standard 5-card draw, if you were randomly just passing out cards, 48 times out of the 2.6 million-ish card hands, that could occur. And I think we figured out that percent, that decimal was like 0.019, I want to say, or 0.0102, or snowball chance in, something of it occurring. So, like I said, you start playing with the numbers of what you have versus possible outcomes. This is why people start to think these numbers through. So, going to the deck of cards, what was the probability that you guess the right card? Guess it. So the probability that you guessed the card correctly was what? 1 out of 52. And for those of you guys who are in here, you just saw,
That was crazy.
yeah. Yes. You ready? Guess the card.
How do you think about the 3 spades?
No. No, Tara was able, Murph dog! Tara,
Yeah.
you know her. She yells Murph dog every day.
She was
It's-
my weapon.
she's great. She walked in here and we were talking about cards. I said, all right. And I asked her to pick it, and she said, Queen of Hearts. We went, Queen of Hearts. And she was right. You have to guess a card to come in. What was it? Wrong. You have to guess a card to come in.
Oh my god.
Say Ace of Spades.
Huh? Wrong. It's the Queen of Clubs. You have to guess a card to come in. Wrong. Queen of Diamonds. You have to guess a card to come in. I have a reason for doing this. I'm going to show you why. Wrong. One more. I'm really yelling even though you can hear me fine. No. But I feel bad for you. So, what I was doing there, guys, you have a 1 in 52 chance of guessing the right card. You have a 1 in 52 chance of guessing the right card. Now, I didn't really reshuffle each time there, but let's say in theory I did. When I asked her to guess a card, and she said,
Queen of Diamonds.
wrong.
Yeah.
When I reshuffle it into the deck, is the next time I ask her to guess a card independent of what she just did? Yes.
2 of Diamonds.
I saw that.
Ooh, I did not see that.
Okay. So what happens here is we'll start to talk about what are called compounding probabilities, where you can have more than one. Each time, each succession, it multiplies itself through. Think of the idea of flipping a coin. Flipping a coin, you get heads or tails, correct?
Sure.
So the probability of guessing heads 2 times in a row is, well, 50%, 50%. Multiply them together, you get 25%, 1 in 4. Same idea here. That's why each of these multiply themselves through, because each one is an independent choice. With replacement or without replacement. So if I didn't put that back in there and I said pick a card, it would be 1 out of 1. And that's what we start to do more of tomorrow. Okay? So what about this? What's the probability of guessing a heart? 1 out,
13 out of 52.
13 out of 52, because remember there are 13 cards in the deck that are hearts, and there's, right, because you start thinking of it a couple of different ways. If you're thinking about just picking a heart, well, 1/4 of the deck is hearts. Okay. What if I say the probability of picking a 2 or a 7?
26 out of 52.
Whoa, whoa, whoa,
Wait,
whoa.
whoa, I don't know what I did.
How many 2s are in a deck of cards?
4.
How many 7s?
8 out of 52.
So what's 4 plus 4?
8.
Oh,
So
you can't just say there's 13 cards and there's 13 cards.
yeah, but I'm just showing you how it goes from the top. So, all right, I'm gonna say 2 or a 7. Ready? I lose. Nope. Okay. That's what we're looking for. Now, to take this back a little bit, you can also do stuff that's called experimental probability. Experimental probability is stuff that you have seen usually in a science class or on standardized tests. This is when you see charts. And I don't want you to write all this stuff out, but you're looking at table. And if I'm looking at this table, what's the probability of a randomly selected person being older than 45? Or I should say 45 or older.
It's like whatever it is.
Yeah. These types of questions are ones that I know that are usually on ACTs or SATs, where they would say they're looking for specific probability ranges. They'd say, what's the probability of selecting a person that's 24 and under or 45 and older? You're looking at what is the success, how many of those would give you a success versus the total possible outcomes. Which basically is reading the chart and adding up some numbers. So if I want to just go back to the first one I said, the probability of getting somebody 45 or older, all I'd have to do is add up the 55,446 and the 34,076, and then divide that by all 4 of those numbers added together. Is everybody okay with that? That's when you start using the experimental probability, because you're using real data to drive stuff like that. Yes, sir.
It's close to 33%.
Okay. So you have where is it 80,000?
89.
Okay, yeah, 89,000 and change over 170,000.
267.
I was so close.
Yeah,
I'm really not going to add that in my head because that just hurts. Okay? I know you guys have done this. I know you guys have seen this. I'm not too worried about how this sets up. But one of the things that does come back is geometric probability. What do you mean, oh? You guys did geometric probability last year.
We did?
Yes. Geometric probability. Geometric probability
I can't draw more circles.
Geometric. It's the, you take the area of the favorable region over area of the whole thing.
Also, like, what's the probability that you'll hit?
Yeah, what's the probability of landing in a red? What's the probability of landing with those reddish orange rings? The area formulas I'm going to make sure that you guys have or that you'll use, I'm not going to give you like a trapezoid. I'll give you circles and regular polygons. Okay? And I have an example of both of these here in a second. It's just perimeter graph. Well, you can if you want.
Oh, this
I volunteer.
I have one of those at home, except it's bigger. No, it's
I actually have.
No.
They're like that.
You actually got her head.
Very upset the sound didn't go off though.
You're like, exactly.
Sound. Of course there's sound.
Why not?
You broke it.
maybe your sound is off.
No.
Pac-Man does it.
How much time did you spend on this?
I feel like you should shoot it in it.
Okay.
Well, I still landed the red. I'm pretty
Now
good.
clone it. See if you're really talented and clone it.
Yeah.
Alright. One of those buttons would work.
Someone go up there and tap it.
Anyway,
Go, lose.
so
Very fast.
I've had a smartboard for a long time. This is one of the very first things I ever made. It's pretty awesome. When we first got, and I told you guys this stuff like this before. When we first got smartboards back at the old building, oh geez, that would have been 7-8 years ago now. The older smartboards, if you remember, if you ever used one at the old schools, they had a pressure sense to them. So it's kind of like touching the side of your thumb there. Whereas these are hard boards. There's cameras. They're all camera sensitive. The old boards, if I shot an arrow at it, it would immediately know that I hit it with an arrow and it would go off and do all that stuff. Whereas the newer style boards, I haven't quite figured out a way to get that thing to hit there and just work. So I'm kind of thinking I might need to just get a Nerf gun. So
Can I bring you tomorrow?
it's a gun. I don't think those are allowed. So let me bring a Nerf gun. I'm just saying. Okay. Yes, sir.
You can get like a different bow and arrows.
Yes, I have one of those at home. Of course I have a Nerf bow and arrow. Moose wanted one for his birthday, so he got a Target gift card, went to and said, I want that. Alright, so back to this real quick. If I wanted to have that probability of landing in the red, which we already know that I win because I got and I landed in red, so the probability of me doing it is just 1 because I'm awesome. You guys are all just worthless. But that's okay. Which means you have to remember how to find. Sorry, I apologize for being so mean. Remember, you have to remember how to find areas of shaded regions. When you're taking the area of a shaded region, you're taking the whole object, and then you got to subtract the inside. So if I bring it out to the outer edge here, I have a 3, 4, 6, 7, 9. I have a radius of 9. So the circle would be a 9 squared pi. And then I'd have to subtract the 7 squared pi just to get the ring. That gets me what?
Never mind.
Okay. To go to the next one. 3, 4, 6, radius of 6. Subtract out the inside of 4,
Where are your traces?
radius of 3. What's 9 squared? Yes, ma'am.
I was gonna ask, couldn't you just do like the whole thing and then add up each individual reason, please?
Wait, 6 minus
This is
4
in
is.
the area.
Wait,
Well, I'm finding the area of each individual. I'm finding the area of each red ring. All right, so I get 81 subtract 49, 32, I believe.
Yeah.
So this first red ring here is 32 pi. The next one is 36 subtract 16. And the last one is 9 pi.
Oh, no.
So the favorable areas would be 32, 20, and 9. I add those together. So the favorable region, 52 and 9 is 61. The whole thing had a radius of 12. 3, 4, 6, 7, 9, 12. So it'd be 144 pi. Now, when you put that in your calculator to get a simplified fraction or the decimal equivalent, just get rid of the pi's because pi divided by pi is 1. Unless you use the fraction bar. Because if you don't use the fraction bar and you put it divide by 144 pi, it'll accidentally multiply it, you'll be wrong. Okay? That's how these work. Which leads me to reminding you of your best friend in the whole wide world.
Bows and arrows? Can I
Nope.
calculate?
Perimeter apple.
What?
Apple, potato, potato. So when you find the area of the shaded region here, if I want to find the probability of landing in the shaded region, we have to remember what, well, a lot, because geometry was a year ago and, you know, that's hard. So one of the things I want you to remember is that when you have a regular polygon that is what we call inscribed in a circle, when something is inscribed in a circle, it means all the vertices lie on the circle. So that means that I can draw from the center to a vertex and it becomes a radius. So when we have ones like these, my shaded region, the probability of landing in the shaded region, yes ma'am?
What's this called?
Regular polygon. I'm getting there. I have to take the area of a circle, subtract the area of the regular polygon, divided by the area of a circle. Now, when you're working with regular polygons, it's been a while for you. Those formulas were always 1/2 perimeter apple
Wait, why did you divide it by your?
with the whole shape, the big shape. The shaded region is created by a circle cut out of a hexagon.
Oh, so
The circle, or hex, yes, circle cut it out of it, yeah. Now, I do perimeter aptitude problems probably a little bit different than some of the other math teachers do, because no matter what, anytime you have a regular polygon, there's always going to be 3 sides connecting somewhere. Whether it's a pentagon, a hexagon, nonagon, 12gon, 33gon, whatever. There's always going to be somewhere along the lines 3 sides connected. I don't draw the whole thing because it's a waste of time. Because what I'm going to do is draw in my apothem, which is from the center to the side. It's the perpendicular bisector of the side. So if I start with 16, I know as I come around 8 and 8. And then I always work on the outside angle in. How many degrees does it take to get around an object? 360 degrees. Regular polygons means that all your sides and all your angles are the same. All the interior angles will be the same, as well as all of their exterior angles. So if all the exterior angles have to add up to equal 360, each one of them will be 60. Take 360 divided by the angles, and you get 60 on the outside. All right? Number of sides, 360 divided by number of sides is always your exterior angles, regular polygons. Using supplementary angles gives you 120 in here. The radius always bisects that, which conveniently gives you a 30, 60, 90. It conveniently gives you a 30, 60, 90 triangle at that to the base. You have an apothem now of 8√3. You have a radius of 16. You now have enough information to figure out the entire problem. What's that? Now we can math. So we have the area of the circle, 16 squared pi. Subtract out the hexagon, 1/2 perimeter, 6 sides of 16 times your apothem, all over your circle. Okay. This is all stemming back from geometry. Okay. It all stems back from geometry. And I know it's probably a year and 3 weeks ago from when you guys did this. Because I know Seb's class just finishing up their project, which means they had a new perimeter apothem right before it. So, right. But even the regular other geometry classes, we're all right about the same. It was just roughly a year ago when you did this. Okay. And that's how those things work through. What's that? Yep. PA is your perimeter apothem. Okay. And then you said throw that in the calculator. Remember, fraction bar. Hit the right arrow when you put your radicals in. And that's about as goofy as this stuff goes. We'll compound it tomorrow. Independent, dependent events. We'll use things of combinations. We can do stuff where if you put your, do you guys still even use an iPod?
Yes.
Okay. When you have an iPod, if you've got, say you have 1,000 songs on it, what's the probability of your 4 favorite songs coming on in a,
One out of two.
but the order matters.
One out of two.
So it would be like,
So-
For that problem, I just got
2 and 1.
No.
It doesn't matter.
You have 1,000 songs, choose 4 over
Yeah.
1,000!
That's understandable.
I'm sorry, you okay?
Like, everybody's getting negative numbers.
For this one?
Yeah.
Alright.
I got negative 1.2.
Did it wrong.
I just sent you an announcement.
Well, I thought it didn't matter. Like, see, this one, it's just like way out of my
Why are you?
Oh, you have to put the pie? Well, yeah, you need to like a pie. Well, I thought you said the pie
One of
was
the parentheses.
What?
It's
Oh.
Well, what's gonna happen there?
Oh, you know, all discombobulated. Cannot simplify over addition, ladies and gentlemen. That either. Addition is subtraction. Subtraction by adding negatives.
Well, now I got negative 2.
It's done wrong.
Oh, I put pie in the sense.
Lamont, let me ask you something. I don't mean to put you on the spot, but
Who really put them in a row?
I
I
just, you're just kind of like,
Yeah, I know, but that's just like, if you were to do,
you're right, that's what it was. Sorry to scare you. It's just
like a little bit, no.
do those, please.
Did we turn in the
There was like one problem on it, no, there was two of them, where like I think I flipped it for the, where it gave you like the answer.